So we're in section 12.4, which is cross products. And we're just going to finish up the notes here. A few odds and ends to handle. We have the triple product. So what is the triple product? When we have three vectors a, b, and c, we define the scalar triple product as vector a dot with the cross product of b and c. So of the way you would actually calculate this, it can be done instead of doing the order of operations by just determining the determinant of this 3 by 3 matrix. This follows from property 5. If you're interested, you can look at the book to see why. So we'll just take this for granted and move on. Why do we care about the scalar triple product? Well, first of all, it has geometric significance. The volume of the parallelepiped, determined by vectors a, b, and c, is the magnitude of their scalar triple product. Alright, so this is how we would calculate the area of a figure that looks like this, and it's called a parallelepiped. So anyway, this also has significance later on in the course. It's not just, hey, look, we can take the volume of this cool, I guess, parallelepiped. So it will have some applications later on. But anyway, just getting back to this, the volume is going to be the magnitude of the basal area, which I've shaded here in gray. So notice that you could think of that as the cross product, its magnitude, because we had talked about already that the volume of the parallelogram defined by those two vectors is the magnitude of the cross product. Alright, so we got that going on, and then we had to multiply by the height. And so the height of this, again using some trigonometry, we can go ahead and do the right angle trigonometry with cosine, and then plug that in, and we got a little formula with that, including that dot product formula that has a similar looking formulation as part of what we have. Then we can go ahead and write this as the triple product. So before I get too far here, I'm going to paste in this image. This is a mineral called calcite, and this is, I believe, one of the forms, crystal forms, that it can crystallize in. I come from a geology background, so when I see that parallelepiped, I think of calcite. And by the way, just a kind of random thing here, when I was Googling this image, this came from an article about how Vikings supposedly use the optical properties of calcite to navigate in cloudy weather. So I didn't have time to read that whole article or fact checked it, but I got a little distracted for a little bit. It seemed pretty interesting. So anyway, there's certain optical properties when you have different angles with the crystal structure. Alrighty, anyway, let's get back on track here. Alright, here's another question. What if the magnitude, or just even the value of the volume of a parallelepiped, or the scalar triple product, sorry, I had to think about the order of those words. What does that mean? When it's 0, is that anything special or not? So when the volume is 0, that's kind of special, right? It means that it doesn't actually have volume, or there's not enough dimensions to account for that. So we can actually come to that conclusion here. When you get the scalar triple product being equal to 0, what that means is that the vectors a, b, and c are coplanar, which means they actually lie in the same plane, and you're not throwing in that 3D component there in any meaningful way. That they're not out of plane from one another. They're all in the same plane, or in other words, that parallelepiped has 0 volume. It doesn't exist as like a real figure, real 3D object. Alright, so anyway, here's a simple example, just like how we would do a problem with some numbers in here. So using the scalar triple product to determine whether the points A, B, C, and D lie in the same plane. Alright, so first of all, kind of like we did for a problem up above having to do with a triangle, we're given points. It's useful to think of vectors so then we can do things like find cross products, scalar triple products, etc. So there's lots of ways you can go about doing that. In this one, I'm just going to define vector u as AB, vector v as AC, and vector w as AD. So having some understanding here of what the scalar triple product would tell us and how we'd want to construct that, we can just look back at our picture here and note that we have one point here that would be unifying these three vectors, and then we're using different points to make those vectors. So you do that, and then you can start doing the math. So the scalar triple product, I told you initially, can be found by the 3 by 3 matrix. So we've kind of done this, but maybe, especially if you're not fluent with matrices and determinants, then note that you can do the same type of thing, but instead of having I as our component, that we do have, in fact, a value 2, and so our answer is a scalar. It's not going to be a vector. Otherwise, this looks the same as when we did a cross product, and so we just do the resulting determinants of the 2 by 2's, and we keep going until we get a value. So because we got 0, just note that we can determine whether the points lie in the same plane, aka whether they're coplanar or not. And the answer to that is they are coplanar, because we got a triple scalar product of 0. Our last thing we need to talk about is torque. So this is an application of the cross product. Cross products occur often in physics. We got a special tau for that torque, denoting torque. And it's a vector. Measures the tendency of a body to rotate about a point, which we often call the origin. The direction of the torque vector indicates the axis of rotation. So here in this picture, just to kind of show a schematic of what's going on, what that means, we have a constant force acting on a rigid body at a point. So we got that going on. And then R we're defining as the vector connecting the origin to the point F is acting on. So that's what's shown in the figure at left. Then torque is defined as tau as a vector is equal to R cross F, where of course R and F are both vectors. Another way to define our torque based on our cross product definition in the geometric form, if we're looking for the magnitude, is the magnitude of R times the magnitude of F times sine theta. So moving on to an example, a cyclist applies the brakes to a cruiser bike by applying a downward force of 20 pounds on the pedal when the crank makes a 40% angle with the horizontal. The crank is 6 inches in length. Find the magnitude of the torque at P. So we have our formula, or actually formulas, for torque. Note here that we're finding the magnitude of the torque, so if we wanted to go ahead and directly use that formula with the sine theta in it, we could do that. We got an angle here, so that might be appealing. So looking at this scenario, first of all, are we just going to plug in the 40? Maybe. Let's compare it to our image up here. And notice that we have the crankshaft here is like our R up here. Our force is a little different angle. And then notice that the 40 degrees is at the same angle theta that's shown here, that's defined in this definition. Or is it a little different? So I let you think about that for a minute. It is a little different. And so in this next picture I tried to draw a little bit simplified version of the picture here. And noting that we can do some geometry here and we have corresponding angles of 40 degrees, and the angle made with the force vector and the vector r is actually 40 plus 90, and that's analogous to theta up here. So that's the angle we need to use. So a little monkey wrench thrown in there, but hopefully not too bad. Applying the formula, then we're going to use 130 degrees. The magnitude of r and f are given, so that's pretty simple. Plug and chug. Units will work out, I promise. Won't lead you astray on doing a calculation with units that don't match. So we get 7.66. And the units would be pound-feet, which again I'm not going to require you to worry about that. That is it for section 12.4.